we decided about a decade ago to start studying turbulence in that tiny little drop of superfluid that is the Bose-Einstein condensate. And that's what I'm going to tell you today. I'm going to show you some, I didn't know exactly what level should I go. I'm going to a level that I'm telling you what I know. So I always imagine that my audience is much more smart than I am. So I put in a level, but I always can speak in a way that you can understand, because I'm not going to say anything that's absurd. So I'm going to stick with the physics that's very intuitive, okay? Even though I'm going to put some relations. But you know that for physicists, intuition is more important than the formula. Okay, so I'm going to tell you first that turbulence is all around us. You know, all the breathing system has turbulence, otherwise it could not exchange the gas in your lungs. The blood circulation has a lot of turbulence on it. The universe has a lot of turbulence on it. The earth has a lot of turbulence on it. Turbulence is everywhere. Our life depends on turbulence. If there wasn't turbulence, we could not breathe. We could not efficiently exchange the oxygen and things like this. But even though turbulence is not well understood yet, you know, there are many, many people that investigate, but we do not understand everything. In the classical fluids, we do not understand everything because it's complicated. But in the quantum fluid, there is a chance that we may understand a little more than in the classical fluid. Reason being that in the quantum fluid, things are quantized. It's not everything possible. Only a few things are possible. And then this is what I do. I study the turbulence in this regime. I study the turbulence in BEC, trapped atoms that are cold to almost zero temperature, such that only a few quantum states are occupied, and they show the traditional superfluidity. And then a Bose condensate can be used for many, many things. I just list a few here, but as you know, Bose condensate has been a workbench for many, many fields of physics in general, including field theory. You know, I think it's the only way we can demonstrate the spontaneous breaking of symmetry and things like this. So it is a very rich field, but because it's a superfluid, we can generate vortices. And by generating vortices, we can put many vortices. And when we put many vortices together, they make a mass and they go to turbulence. So this was the original idea. And then just a few remarks about the vortices in a condensate. When you stir a condensate, you generate vortices. And as you know from the basics of quantum mechanics, the vortices are quantized. Each atom cannot have a different angular momentum greater than an integer number of h bar, which is the Planck constant. This is the principle of quantum mechanics. And therefore, the vortices are really holes very well established in a condensate. So when we stir or we make any rotation, we generate vortices. And vortices are quantized. The velocity field of the vortex of the fluid is quantized and follow a rule that the circulation, which is the integral of the velocity around the vortex, is an integer number of h divided by m. So this is great because instead of having a big mass, I have tiny little holes that I can deal with. And people from MIT, from Cornell, and from England, they've been doing many things related to vortices in BEC. Okay, and the vortex, because the rotation is there, there is a hole in the fluid, in the center of rotation, as any other fluid. So you see a hole, and the size of this hole is related to what we call the healing length in quantum mechanics, which we're not going to deal a lot with this, but it has to do with the density of the fluid and the interaction of the atoms, which is this little a you see on the bottom. Okay. Now, there are many things that are important in turbulence, in general turbulence in any fluid, which is randomness, You need a dissipation, some kind of dissipation. Energy has to go everywhere, has to go somewhere, I'm sorry. You need what they call cascade, which means the energy will flow from dimensions, different dimensions of your fluid. And we have what we call scaling, which means the property will scale with the dimension and with the momentum in a very specific way. The most important scaling law that we know in fluids and turbulence is called the Kolmogorov law. And the Kolmogorov law says that the momentum and the energy spectrum, so this is the E is the energy spectrum and K is the momentum. So it says that the energy is distributed in momentum in a way that obeys a law that's called Kolmogorov law, or is the famous law that goes with the minus 5/3, as you see in the picture. So this is one of the most important things people know about the regular turbulence. And of course, when we go to the quantum fluids, this may not be exactly like this, because this is true for water, but there are a lot of new things in the quantum fluid that we may learn. So this is a picture of one of the laboratories. We have 3 laboratories here in São Carlos in Brazil, doing study of excitation of the condensate, which is a tiny little drop of superfluid, to see the appearance of this turbulence. When we do some excitation, you can see that we make a hole on it, which is the vortice. So we introduce a tiny rotation, it makes a vortice, and then we make many vortices, and that's evolved to turbulence. And I'm going to try to show to you how we study this. Oh, I have another experiment. We try to combine 2 different superfluids, potassium and sodium all together, because we strongly believe that we'll be able to produce turbulence in one and eventually transfer to the other. Turbulence is normally taken as a very uncontrollable thing, but we believe that in the future, in the quantum sense, we'll be able to control it. So this is very exciting. Okay, so quantum turbulence is being studied in many senses. Classical turbulence even further, centuries of study. Quantum turbulence is newer. Richard Feynman start to talk about quantum turbulence, or turbulence in liquid helium, which is a superfluid. It is a quantum system, and then start to study, and there are many properties they could study. But then we discovered that going to the condensate, we can go even further, because the condensate, first of all, we don't need a big tank of helium. We need a tiny little drop with 1 million atoms. And we can do much more in a tiny little drop than we can do in the tank of helium, liquid helium. Like we can produce films, like a 2D system or a 1D system, or we can control the interaction. We can do many things, and we can mixture different superfluid and see what's happened in the interaction of so much chaotic fluid, superfluid with another one, and so on. Are you understanding me well? Good. Okay, so when you make those vortices in the superfluid, there are many things that can happen. One of them, those vortices, they come and they cross each other. This is called a kind of reconnection of vortices. And then you have 2 vortices, which is 2 lines coming together. They react, and then you can see they start to wiggle. They start to have wiggles on the vortices. And then sooner, when they make many of these reconnections, you have a big mess. It's like having a tangle configuration of those vortices. And this is what they characterize the turbulence. And this is the kind of thing I'm going to do and show to you the properties. What's happened when the superfluid is so filled with those vortices that they make this tangle configuration of quantized vortices, then they lost the property. Intrinsically, there is always the interest to understand how this disorder goes in the quantum system. We all learn from young kids that quantum system is so well organized, energy is well discreted, States are well established, but here comes a mass. So let's see how the mass is in this quantum system. Okay, there is one very important thing in turbulence, any turbulence. You put energy in the big scale, like making big vortices, the one you can basically see by eye. But then that energy, because of those reactions, start to migrate to a small scale. And the way they do that is by those reconnections. By doing reconnection, they start to have wiggles on the vortex lines, and more wiggles and more wiggles. Suddenly, you get wiggle on the size of the atomic system. And then you have the phonons. You have a vibration on the atomic level, which are the phonons. So we could say that the turbulence in the superfluid ended by emitting sound. Maybe we can make a music out of it, because that's the way the energy goes and migrates to the very short scale, to the very large momentum, because momentum is the inverse of where the energy is. So if you have energy in a large scale, it's a small momentum. If you have energy in a tiny scale, it's a large momentum, because momentum, as you know, is the reciprocal of the real space. Okay, so this is called a cascade. And if there is turbulence, normally people say that should be cascade. And there are many types of turbulence in the superfluid. And you guys in England made a big contribution in understanding all the types. But we have what we call Kolmogorov, which is a kind of classical. Because when we have many of those vortices, they may tangle together, make a bundle. And the bundle of quantum vortices behavior more or less like a classical vortex. So it obeys the Kolmogorov relation, which is valid for normal fluid. But you can have what they call the Wiening, which are, I think is closer to what we have. Vortices that produce all those tangle configuration. This is called super quantum. And then because we can shake the condensate, it may have waves on the surface, the density waves, and that's called wave turbulence, which also has a big interaction of those waves, because they condensate, they have a big interaction, nonlinear interaction, and that makes a mass. Every nonlinear system likes to make a mass when you make interaction of excitations. Okay, so there are three types of turbulence that we consider and we study. So now comes the real life. I have my condensate and I'm going to excite it. How I do that? Well, I create what I call a washing machine for those atoms. The washing machine, everybody saw a washing machine, right? The washing machine do not rotate, it shakes. So together with shaking the condensate, I add a little squeezing and deformation. And this I do by magnetic field, because we trap the atoms by magnetic field. I'm not going to elaborate on that, but the internet is filled with information on that. And then when I start to shake my condensate, I start to see vortices being formed, more vortices, and suddenly, boom, turbulence. And then this is what I'm going to show you. The history, what I do with my poor condensate is in this line, bottom picture. I produce the condensate. I do all kinds of evaporation, everything, produce the condensate. And then I excite, boom, 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 shaking that way. Well, when I say shaking, it's not like I'm doing, condensates are very delicate. You have to shake it very tiny, it's a kind of very tiny shaking. And then I produce the excitations. Then I wait some time, what I call holding time. And then this is very tiny, it's like a few microns. To really see what's going on, I have to let expand and observe. So I do what we call a time of flight before the image. And what I see there? Well, I see vortices being formed. Suddenly I see a big mass, which is the turbulent regime. And now I'm going to start to characterize this turbulence. I'm going to start to characterize what's going on. And we did something very interesting. We go even beyond the turbulence, and we saw what we call granulation, which is the superfluid breaks in domains of tiny little drops. And we have a good explanation for that. Okay. So first of all, we try, the way we do is excite. And we need a frequency to excite, and we need an amplitude. And then we map everything that happens to the condensate as we combine amplitude and time of excitation. We kept the frequency fixed for this type of study. And we observe first, there is a kind of motion of the condensate, which is this tiny drop that's called bending mode. And Chris Foote from Oxford, a brother University of Bristol, that studied this very deep, study what's happened to the superfluid when you excite and you see this bending mode. But then this tiny rotation I introduced are so strong that vortices start to appear. And then I keep pumping energy. You know, when things start to be messy and you pump more energy, they go even messier. So I reach the turbulence in a domain. And if I keep putting energy, I get to what we call granulation, which is a breaking in domains of this superfluid. Of course, we are dealing with a many-body quantum system. It's a system that obeys not the classical law, but the quantum law. So we are dealing with everything you learn in school about this quantum system. If I follow the number of vortices in my system, tiny little drop, you know, you cannot put vortices occupy a space, as you can see. I cannot put an infinite number of vortices. There are a finite number I can put in a drop of condensate. So I see the number of vortices increasing, suddenly stops. There is no more space. The only chance they have is react. And then the turbulences start to evolve. And then I see the vortices disappear because it's so much energy distributed that we cannot identify the vortices anymore. They break up and probably we evolve to big fluctuations of the density of the system. So you following this, Orlando? You is okay? All right.
I think so.
So, good. You know, everything in physics, we need to characterize how the energy is located. And this is what we call the energy spectrum. The energy spectrum is E of K, and K is the momentum of the atoms, right? So we need to know how is that. And that is called the energy spectrum. And this energy spectrum characteristic will tell us what's going on there. So we gotta measure the energy spectrum. So I have to know where is the energy in terms of momentum. What is this relation? And the way we do that, we use the two different approaches. One is, well, if everything is energy in my system, I break down the potential, I let my atoms to fly out, and then I measure how many atoms will reach farther distance. And then I know the momentum they have. This is called time of flight technique. And with that, you can measure the momentum distribution of the atoms. How many atoms are in each class of momentum? This is called the occupation number of momentum, N of K. And then each atom must have a K square. Remember, the energy of the atom is the momentum square divided by 2 times the mass, because this is a kinetic dominate system. Then I can get to the energy spectrum. Or I can do something more complicated. I do a power spectrum. Power spectrum is something a little more elaborate, because they say that the fluctuations of the velocity is what really, with respect to the average, is what really constitutes the energy that is in there. So I have to measure the fluctuations of the momentum field, correlated, do the Fourier transform, and get to the power spectrum. Don't worry about this. Those are technical details. You can find that in any book that you take from the library or from the internet. They're gonna have. And normally we refer to the Wiener-Cincini theorem for getting the power spectrum. This is very famous in electrical engineering. because in electrical engineering, they have to know where is the energy, in what frequency, in what momentum they are. So that's what I do. So this is a picture of a turbulent condensate. I let expand, and I measure how many atoms reach farther by just mapping with the light and absorption. I see how many atoms are there. And then I have exactly the momentum distribution of the cloud. But this is, when I do this, I have to make an absorption of an optical field to be able to know how many atoms are in each position. And then it's like projecting the cloud in a plane, which is my detector. And then I have to recover the three-dimensional momentum distribution. But thanks God, physics has solved all that. And we have a transformation that's called Abel transformation that allow me to go from a 2D projection of momentum to a 3D. And I do that, and then I can get the momentum distribution. And here I put some typical sizes of the cloud before I put it to expand. My cloud looks like a cigar, which has about 3 microns across on the short dimension and about 50 microns on the large dimension. And I let it to expand a little bit to be able to see and to measure the atoms. Otherwise, it will be very dark because the density is high. Okay, when I do that, I get plots like this. When I just have vortices in my system, and I measure the momentum distribution, I don't see big change. But when I go to turbulence, I see a big change. First of all, the distribution goes towards higher momentum, which means atoms goes to getting energy in a small scale. And they start to get a very interesting feature here. And if I go and calculate, I get a slope. I get that there is a region that they call inertial region where I have a power law, which power is -3, which is a kind of Kolmogorov type relation, showing that indeed this is a turbulent sample. Okay, and then I do the same. Oh, this is how it looks if I plot the momentum, because when I let this expand, I just measure in momentum, right? Because the distribution is now a distribution of velocity of the atoms, or momentum. We like to say momentum. On the other technique, I have to take many pictures. I have to repeat my experiment many times, creating an ensemble of pictures. And then I take the average of this ensemble. And of course, when I take the average, I kills all the fluctuation. And then I subtract this average from all the pictures. And what I get is an ensemble of fluctuations. And by looking how much fluctuates and how far is one fluctuation from the other, I can get what they call correlation. Is if I have one here that's fluctuating, if the next one is fluctuating as well, and so on. So by doing that, I can measure this fluctuation spectrum, fluctuation function. And then by doing the Fourier transform, I get the power spectrum, which is the energy spectrum of my system. And then you see that as a function of my power, of my amplitude of excitation, I get the distribution, my spectrum of energy being distorted in agreement with what I expected from a turbulent regime. So basically, we get to the energy spectrum. And on the top of it, it's like you can see how those clouds look like for different amplitude of excitation. This number on the top is a number that's proportional to the excitation. Okay, but again, at the end of the day, we must have the two techniques agreeing, otherwise we're not measuring the right thing. And they agree. either with the power spectrum or with the time of flight, we get the same energy spectrum of the cloud. And the dependence with the K in the regime that we call the inertial regime, this is what characterizes the turbulence, is this -1 exponent. And then we are happy with this. And we believe we have a very nice turbulent. Now, what kind of turbulence we have? We may have what we call the Wiening super quantum turbulence, which is that big entangle of vortices, or we have many fluctuations, wave densities, propagating and interacting in the condensate, giving rise to this turbulent regime. They both have a very similar power spectrum, and at this moment we could not really differ them. We believe that it's more towards the wave turbulence than the super quantum turbulence. But because we see the vortices in the beginning, it must be not waves, but because of those stronger reaction of the vortices, they must, or they could, change into waves, big fluctuations of the cloud, of the density. Well, we are worried about the isotropy. People say that the turbulence should be isotropic, but we see very non-isotropic kind of randomness distribution of the fluctuations, but they always, it doesn't matter in what direction you look, you always find the equivalent behavior. So the main aspects of the turbulence are indeed the isotropic, even though the cloud itself is not. So by looking in different directions, Y or X on my cloud, on the momentum distribution, I see equivalent. In black, you see in blue, and in red, you see the two different behavior in different directions. But the average give the black one, but they have equivalent type of behavior. Okay. Well, let me jump this. This is a little bit too mathematical because I told you that the energy flow on the momentum scales. So before I put the energy in big vortices and suddenly I see tiny fluctuations. And what we try to do is measure this flow of energy going through the momentum classes. And then you have to start what we call the continuity equation. The variation of the density of atoms in the momentum space is related to my injection of energy, my dissipation, and whatever comes out from this region. And because this does not dissipate, and I'm not injecting any more energy, after I excite, I stop, the I and D term are zero, and then I can do some mathematics to show to you that we can really see the energy flowing naturally from small scales or large from large scale, small momentum to small momentum, or to large momentum or small scale. And the way to do this, we can prove that this flux of energy is related to the variation of the integral of the energy spectrum. So we get the energy spectrum. This is the energy spectrum. For different times, I see how it varies for each K, and then I can calculate the flux. And we have done this to see that there is a region where the flux is constant. It's like the energy starts in one scale and flow without dissipating to a small scale, which is a very important characteristic of this quantum turbulence. Okay, I'm gonna jump to this. And because you guys deal with chaos, right? This is the name that they gave me, that's a club of chaos. We like to characterize the disorder, and we do the measurement of the entropy. And we use what they call Shannon entropy, which is basically related to the fluctuations of the density. And we measure that as a function of the amplitude we excite. And what we see? we see that the entropy is more or less constant. Suddenly, boom, when the turbulence takes place, the entropy blows up, right, as expected. Okay, and then we can show also that even if you wait, the turbulence, the entropy will grow because those reactions are going on and more disorders being introduced in the system. Well, I put in some references, but in my homepage, I have a lot of references for that. So we study and we believe that the entropy is a nice way to characterize the turbulence as well. Normally people don't like to do that, right? But we believe that that's a nice way of doing it. And more recent, we came with this integral scale length. Well, this is traditional in turbulence, but we can measure. The idea is, where is the energy located? And if the energy is migrating, it should go down, right? And this is what's happened. The energy, if we calculate the integral of the energy spectrum divided by K, it's like getting a length. And this characteristic length is where the energy is mostly located. And then we can see the evolution of the energy flowing from the big, all the fluid to a small scale. And we can find out how is the decay of the turbulence and things like this. This is where we study. Now, I want to get my last few minutes to explain to you, what can we do with this turbulent cloud, right? I think this is an interesting question. You know, turbulence is complicated enough, but empirically it's very nice. It's disorder, nobody understands. So it's nice. It's a good thing. In quantum, it's even better because we got to understand and compromise with the quantum nature of the matter. And that's what I'm going to do now. If I have a turbulent gas, okay, one thing I can do is let this go away. Let's propagate in space. But remember, it's quantum. It's not like ballistic motion of particles. Those are like matter waves, you know, the de Broglie waves that we learn in quantum mechanics. Those are de Broglie waves propagating in space. But now they are disorder. How they behave? Well, they behave exactly like when you have a laser beam, which is coherent, and you introduce disorder, you have what they call the speckle on the laser field. And they propagate in a very interesting way, and this giving nature to the statistical optics that people do. I'm going to show to you the first speckle field of matter waves. But then there is another thing we can do. This system is out of equilibrium and has a lot of disorder. Having disorder, we can think about Anderson localization, which is how particles hit each other in this random medium. And the second thing is this complete a mass, or there are some order on this big mass, which is what we call universality type of behavior. So I want to show you the two things, because if I was a young student, I was going to start one of them. Okay, so let me show something very, very bizarre. If you take a classical gas in a balloon and let it blow out, the gas will go to the environment, right? And then in a few, very soon after you blow the balloon, the gas is expanding isotropically, because in each point of the balloon, you had a velocity distribution equal to everywhere. And now, so suppose I have a Mickey Mouse balloon. You know the Mickey Mouse head? If you go to Disneyland, the first thing you do, you buy a Mickey Mouse balloon. Inside the balloon, there is a gas. I blow the balloon, boom. So immediately after starting the expansion, you lose the shape of the head of the Mickey Mouse. You cannot tell by looking far apart that there was a Mickey Mouse. Now, let's imagine that inside the Mickey Mouse balloon, I have a superfluid. If I have a superfluid, I blow it, boom. It does not behave because now I don't have atoms going. I have waves. And whenever I try to squeeze the waves, they diffract. So a smart physicist could come, if I have a superfluid gas inside the Mickey Mouse balloon, when I blow, and the guy collects what's the distribution of gas all around, he could recover the Mickey Mouse head. Because wherever was more squeezed, like the nose or the ears of the Mickey Mouse, will expand faster. Because the uncertain principle, this is a quantum gas. Whatever you squeeze it in space gets momentum. You understand? Very good. Now, let's go one step further. I have a Mickey Mouse balloon. Inside, I put a superfluid, but I put a turbulent superfluid. Guess what's happened when I blow the balloon? It keeps the Mickey Mouse head. It's not that fantastic? Something magic is there. This is called self-similar expansion of a turbulent quantum gas. And we find this in other places? Yes. We find this in laser field propagation. When you have a laser field, you have a coherent Gaussian beam. It's like, you know, all the photons, everything's behave exactly the same. And the waves are all coherent. And they diffract. If you try to squeeze the laser, it diffracts, right? We do that experiment in freshman laboratories. Now, suppose I put a lot of disorder in the field, in the laser field. This is called speckle of laser field. You know, I produce a big interference. When that propagates, it behaves exactly like the turbulent quantum gas expanding. So we're dealing with the propagation of matter wave. De Broglie waves propagating in space. But before, in the condensate, they were like a laser. They all go together. But because of the turbulence, they behave like a speckle. And then I make a comparison between light, laser beam, which laser beam is for light, what condensate is for gas. So I made this very interesting comparison. And of course, they are very equal. They behave exactly the same because we are doing is putting disorder on the phase, random phase and random amplitudes in the matter wave propagating, and happens the same. And even better, we came with an explanation why these things expand in a self-similar way. But I'm going to invite you to read the paper that is in the Proceedings of the National Academy of Science of the United States to understand why a turbulent gas propagates like a laser beam with speckle on it. Because my time is run away and I want to show something even more exciting. So, you know, I am doing what, well, I did a lot of correlation. You see that we like correlations, right? We are crazy. We like to see how one thing changes, if the next change equivalent, and those are correlations. So this is the Bose-Einstein condensation with turbulence on the bottom and no turbulence on the top. And this is the speckle optical field laser beam with a normal Gaussian beam propagating, and now with the speckle. The same thing. That was expected because after all, quantum mechanics is matter waves. And laser beam is electromagnetic waves, so they behave very much the same as expected. Okay, and well, as I told you, we like correlations, but I'm not gonna give you that. They are equivalent to, and we gave a very good explanation. Now, so you see, we produce, I think, one of the first three-dimensional speckle field of matter waves. Why is that important? Because, you know, there is a whole understanding of statistical optics, right? People produce speckles to understand the statistics behavior of the light beam. Now we can do that with the matter waves. So it's the introduction of statistical kind of behavior in matter waves as well. But that is one thing even more interesting. When I produce my turbulent cloud and I let it expand, I see a nice behavior. I do a lot of little tricks, integration here and there, blah, 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 to see the atoms, to see the distribution. And then I measure the momentum distribution. I told you before. But you know, normally in a condensate, you have a core, which is condensate, and then we have a tail, which is a Gaussian distribution, which is the remaining atoms that's not in the condensate. This is what we call the thermocloud. That means that my sample has a finite temperature. Always I see the Gaussian, which is a behavior like e to the minus v squared divided by kt and so on. You all have done that, right, in the undergraduate courses. So that means I have a thermal sample, a system that's in equilibrium. When we do the turbulent, what we find out is that the tail is no longer Gaussian. Even though we are in a finite temperature, we believe that's not Gaussian. What we find is an exponential tail. Exponential is wonderful. I love exponential. In my home, I have the drawing of an exponential plot near my bed. It's really wonderful. It's a wonderful function. Everything is exponential or Gaussian. Come on, if it wasn't exponential, we could not deal with big numbers. It's wonderful. Logarithm and exponential, broader functions, they are wonderful. But when it comes to a system like this, they are trouble. That means that this system is not thermal. I cannot assign a temperature for this system. It's not in thermal equilibrium because of this Gaussian tail, of this exponential tail. You know, to assign a temperature, I should have a Gaussian, like I start with when I don't excite. But after exciting, produce the turbulence, I see a change in behavior of the tail. The tail means the atoms that has higher momentum. It's the one that goes further apart, which is the one that's not in the zero temperature. It's not in the single quantum state. And I see a very nice transition from Gaussian. So this is an exponential, but alpha is a number that can be 2 before I reach turbulence, or 1, which is exponential when I reach the turbulence. Well, this is a very non-thermal system. If it was a thermal system, like in equilibrium, we have the phase transitions. We have what we call the fixed thermal points. The point of phase transition. Everybody knows the transition of many things. It has a fixed temperature, a fixed thermal point. For our system, the indication is that we may have a non-fixed thermal point. And this is a non-equilibrium system because of the exponential tells us. And then there is a very nice theory going on for non-equilibrium thermal systems. How can we deal with this? People don't even know how to deal with the non-equilibrium system in classical gases. Can you imagine in the quantum gas? But a few smart guys came with this idea that when you have a non-equilibrium system, maybe quantum system, maybe it can hang around a non-thermal fixed points. So it's not an equilibrium, but is a point, is a condition on the many-body quantum system that delay the thermalization, delay the system to evolve to equilibrium. So that's why it's called non-thermal fixed points, because the system like to hang around this point. And when the system hang around a point, it presents very special properties. Oh, this is what I'm telling you now. I see that this is an audience of very young students. This is top line topics to get involved in career research if you like quantum mechanics, right? Well, there are many papers that were published, and a picture of these non-thermal fixed points is like, I have my system, my condensate, I excite, it's evolve. So I told you, that is evolution. We measure that. But maybe it hangs around some point and it stays there. It doesn't want to go very far for a while. That's why it's called non-thermal fixed points. It's a meta-stability that hangs around. And then eventually you get out of that point and go to equilibrium again. When you have that, this is the momentum distribution of my non-equilibrium system. We can show that, I mixed it up the order. We can show that some properties of the system, like the momentum distribution, when they are around a non-thermal fixed points, they scale, they evolve in time and space in a very peculiar way. Because you could expect that it is non-equilibrium. This thing is going as it can to reach equilibrium, but when it meets one of those specific points, it has a very specific scaling law. Like we have a lot of scaling law in thermal equilibrium, right? We have a lot of scaling law in thermal equilibrium, but here we have scaling law in non-equilibrium. And then we can show that the distribution of this non-equilibrium quantum system evolve in time. If I know the system in a time t0, I can predict how the system will be in some time t, because there is a specific scaling law with alpha and beta scaling the time and the momentum. Very interesting, huh? Because non-equilibrium is mass, but here is a nice thing inside the equilibrium. And so if you measure those momentum distributions and then you scale them, they all fit in a single plot. So it's like the system hangs around a distribution and evolves following a specific scaling, specific law, the way I showed to you, determined by these two coefficients, alpha and beta. This is a new vision of non-equilibrium system and a new vision of non-equilibrium quantum system. In England, you have important groups in Cambridge and many important theoreticians doing this. You have Tom Gazanzer in Heidelberg. You have important physicists all around the world. And what we're trying to do now is to show that quantum turbulence is one of those phenomena that has those non-thermal fixed points that make the system hanging around. And why is this important? We can predict how a completely disordered system that wants to reach equilibrium will behave, at least for a while in time. And then, of course, we have to understand, which we don't know yet, what makes the non-thermal fixed points exist. This is a challenge. So we proved that those things follow in a single curve when we scale, which means a universality type of behavior. So we have a universal plot to determine, even though it's non-equilibrium, we will evolve following a universality. And that, of course, is can put us in a better understanding of those problems, especially in quantum mechanics, which involve non-equilibrium system. And life is filled with those. We know that life is quantum, right? There is no way of exchanging charge and atoms inside the membranes and everything. And a lot of things goes on there in non-equilibrium. We are not equilibrium persons. Otherwise, we will never get old. But we do. We are evolving. But we have to understand in the quantum level what's going on. And it's better to understand with a quantum system that's closed, is a many-body system, have many atoms, a million atoms, but we can somehow prove things. Well, Eden, I see that you're getting very excited. I was going to tell you about some peculiarities of the quantum system as well, because in quantum, I have to tell this, is also exciting. I told you two excite stuff, and I didn't even spoke about the Anderson localization. But let me tell you this here. When you wake up in the morning, Orlando, and you produce a big vortex in your sink, what's happened to the vortex? It decays away, right? You know, you make a vortex in a small container, makes a big vortex, dies away. What's happened if we make a big vortex in the quantum fluid? Well, because the big vortice is not stable, it decays in tiny little vortices. This doesn't happen in the classical fluid, only the quantum, because the energy of rotation is L squared, the angular momentum squared, divided by 2 times the inertial momentum, right? We learned that in rotation. So it's less energetic if I have this is a vortice that has a 4 h-bar of angular momentum per atom. This one that I'm showing here, you see? It's a big hole in the condensate. And then it drops, it decays naturally because of fluctuations to 4 tiny little vortices of 1 h-bar. And then the system has a surplus of energy in this case. But then because of this decay, has a surplus of energy that shakes the vortices, and then they start to tangle, and they naturally, spontaneously go to turbulence. And that does not happen in the classical fluid. Spontaneous, if I produce a vortice and I did not produce turbulence, the system will decay without having turbulence. But here, the decay of a giant vortice produces the turbulence. And I want to try to show, well, I haven't been measuring this. Let's see if it works. My simulation. Can you see my simulation of the 2 vortices evolving to turbulence spontaneously? Nobody's doing anything. You just produce a giant vortice, but the giant vortice does not like to stay giant and decay slowly. It decays suddenly and produce little kids vortices that reacts and go to turbulence, which I think is very interesting because spontaneous route to turbulence is something that calls our attention. Well, we have many papers. I have my homepage here for you, and there are some papers which are review papers that is not hard to read, and I invite you to do so if you are interested in this topic. And this is my group of research. It's giant. And I have collaboration with many people, including some gentlemen from England, like Carlo Barenghi. And now I have a collaboration with many other people from Newcastle and eventually from other universities, right? And my group is big, but we work in atomic physics, but we also work in biophotonics and nanoplasmonics. And I want to finish this with a very nice phrase. It's not mine. I'm not smart enough to produce a phrase like this, but it's very nice when you give a talk because you see people say the following. I've learning that people will forget what you said. People will forget what you did, but people will never forget how you made them feel. So I hope my talk did not make you feel bad, because I want you to have a good remembering of the talk. Thank you very much, and I hope to see you guys again in another opportunity, probably presentially in England, because I love England. Thank you very much.
Gosh, thank you. Thank you so much. Thank you. I mean, my mind is slightly boggled. It was a very interesting topic and slightly beyond my physics understanding, but yeah, thank you ever so much. And please, if people have questions, do drop them into the chat. We do have a few quickly, if you don't mind sticking around just for maybe 5 minutes. Professor, would that be okay?
You know, Eden, when you see a talk that has a lot of, there are many things that I did not cover in detail. So you have to keep yourself in the things that you understood well, which is, I am sure that everybody understood that we can do turbulence in a superfluid, and there are important challenge problems there for being discovered, right?
Yeah.
Question.
Thank you. Yeah, so if anyone has any questions on something, yeah, then do drop them in the chat. I did just want to ask one thing. What are the kind of practical applications of turbulence. And also at the beginning, you said how to understand turbulence, you may be able to control it, or chaos you want to aim to control. So how is that working?
Okay, we believe, I may be wrong, but we are planning an experiment where we have two superfluids, one made with atom A and one made with atom B. And we can control the interaction between those atoms. So we're going to produce turbulence in one, and then they will be together. We start to turn on the interaction between them. So the idea is that one superfluid will suck part of the rotation field of the first one. And then this will never reach the condition where, you know, it's like I transfer all the turbulence to the other fluid, and then I control the turbulence in the first one. This is an idea that still remains to be demonstrated. And, you know, I've been working this for 10 years. Before I work in many other things on collisions. I work a long time in collisions of cold atoms and, you know, quantum stuff inside the atomic encounter. But I believe that turbulence is one of the challenges, right? If you look around, this is one of the things that mathematics and physics still needed to understand deeply, because everything depends on turbulence, even our life, as I told you. And we are in many situations that we don't know even how to characterize. And what I said is the quantum system is nice because I can do wonderful things that I cannot do in the classical fluid. And besides, there is the quantum ingredient on it. We get to understand how quantum world goes, right? There is no question that we're going to evolve to the quantum level of everything. Biology, computer, right? Computer is almost a reality, quantum computer. So if you want to understand what's going on around the technology in the coming future, we got to understand how the quantum world behavior itself. And superfluids will play an important role someday in the technology. Today is important for many superconductors and things like this, but we got to understand better the whole thing.
Okay, thank you ever so much. I know we have gone over time slightly, but it's been wonderful, and thank you so much for giving up your time to come and speak to us. Thank you.
Well, I appreciate more than you guys. I love to. I didn't know exactly to whom I will be speaking, so I put the transparency in the level, as I said to you. I always consider my audience much smarter than I am, and normally they are. So if I put the too simple transparency, they get disappointed.
You've stretched us, but that's what we signed up to physics for, isn't it? To be stretched. So thank you. Yeah.